Hello, everyone. Thank you for joining us today. I am Matthew, and I am one of the teaching staff for the online class, and Alexander's behind the scenes. I'll ask Professor Impey to give a quick introduction, then we'll start with questions.
Okay, welcome everyone to another live session for the online astronomy classes, and looking forward to your questions. And I anticipate, since the news is just hours old, that there will be something about the Nobel Prize in physics today.
Excellent. The first question is from Cornan, who's on with us live. Given the vast distances of space, would it be more sensible to try to build gigantic telescopes instead of sending space probes to nearby star systems?
Absolutely, because the speed of light can't be beat, and our best spacecraft are a tiny fraction of the speed of light. So even small robotic spacecraft cannot be accelerated to a significant fraction of the speed of light. The energy cost is too high. So we are essentially talking about travel times to star systems that are hundreds of times slower than light will travel. So for investigating these star systems and sending signals or messages or listening for messages, obviously light is the way to do it. Nonetheless, people are planning, like Breakthrough Starshot is planning to send nano probes to the Proxima Centauri system, which is just over 4 light years away, and they think with solar sails and high-powered lasers to accelerate the tiny spacecraft, they can achieve a speed perhaps of 5% of the speed of light. And that would, of course, get you to a system that's 4 light years away, and 4 times 20, about 100 years. They're hoping to do better than that. But it's a century just with that technology to get to the nearest star system. So that's about as good as we can imagine doing with small robotic probes. And light is always going to be quicker.
Excellent. Thank you very much. The next question is from Pat, who has a question about black holes. I think we'll be hitting a lot of black hole stuff today. Is there some reason why, when discussing the Chandrasekhar limit, most writers just say solar masses rather than the correct solar core mass, like a specific mass of a star?
Right. Yes, it's just casual usage, I would say, but it is correct that the Chandrasekhar limit and the transition between a stellar core that either becomes a white dwarf or a neutron star or a black hole, these are limits that apply to the core of a star. And in its life, to reach that endpoint, the star will have ejected mass. Most main sequence stars like the Sun, will probably eject, for example, about 1/3 of its total mass before it becomes a white dwarf with about 2/3 the mass of the Sun. And the stars that end up leaving behind black holes, for example, which have to be at least 3.5 times the mass of the Sun for it to be a black hole, they usually start 4 or 5 and maybe even 10 times more massive stars. So yes, the terminology about stellar cores really just does relate to that part of the overall star. And there's a larger part of the star that exists far beyond an event horizon or a core radius, some of which is even ejected during the life of the star.
The next question is from one of our live viewers. Sorry, I got lost in all of the chatter. So can you talk about why different stars end up with different endpoints? Several people are interested in why certain stars die and turn into black holes or neutron stars. What makes the difference there?
Right, and so in the idea of stellar evolution, mass is destiny. That's the simplest way of framing it. So basically, if you tell an astronomer or a theorist or anyone what the mass of a star is as it begins its life, then the astronomer can predict how it will end its life. So it's really quite a clear linear path. And in that process, of course, a lot of things happen. There's a lot of changes. The star changes its nuclear fuels, reconfigures, undergoes parts of its mass condensing or collapsing to a hotter, denser configuration, while other parts move off into space, such as the red giant phase. But it doesn't matter what the complexities are. The initial mass of a star dictates its destiny. So the Sun, for example, is destined to be a white dwarf because we know it will lose some smallish fraction of its mass along the way, mostly in the red giant phase. And then the core that's left is not of sufficient mass to overcome the sort of Pauli pressure, the exclusion principle pressure of electron degenerate matter, and so it forms a white dwarf state. If that core is beyond the Chandrasekhar limit, which was the previous question, about 1.5 times the mass of the Sun, then the gravitational force is sufficient to overcome electron degeneracy pressure. You have a reverse process of beta decay, so electrons and protons merge or are forced to merge by gravity to become neutrons, and with electrically neutral material there's no resistance to the star collapsing to the density of an atomic nucleus, and that's a neutron star. If the mass of the core at the end of its life is above about 3.5 times the mass of the Sun, then even the neutron degeneracy pressure from the Pauli exclusion principle is not sufficient to prevent further contraction, and that's the point at which you collapse to a black hole state with an event horizon, a boundary from which no information can escape. So all of these outcomes, these three very different fates of stars, are predetermined by the initial mass of the star. It will follow a life trajectory, lose some mass, and then the remnant will dictate what it turns into.
Excellent, thank you. Here's an excellent question that I don't believe I've heard before. Rashid would like to know if dark matter bends space more than normal matter or the same as normal matter of the same density.
If it were equal densities, then the curvature of space-time is determined just by the mass. And so in a global sense, we know the universe contains 5 or 6 times more dark matter than normal matter. So in many configurations, the dark matter is doing most of the bending of light and the curvature of space-time. So it's basically just scales by the mass. It doesn't matter what the nature of the mass is, whether it's visible particles like protons, neutrons, electrons, or dark matter, a particle whose nature we don't yet know. The curvature is dictated entirely by the mass and by the mass density. It turns out that, for example, with galaxies, the dark matter part of the galaxy, the halo, is more extended than the visible part of the galaxy, the stars and gas. And so in that sense, the concentration of the normal matter in the center part of the galaxy means that it will make more space-time curvature in the center of the galaxy. But the halo has most of the dark matter, and so there will be curvature of space-time out to very large extents, far beyond the visible extent of the galaxy. So basically it just depends on how much mass you have in a particular region of space, and you can predict the curvature.
And sort of similar follow-up to that is it possible that there's actually less dark matter than we're guessing, but somehow it interacts more strongly gravitationally?
There's interesting speculation about the nature of dark matter. It is indeed possible. For example, there are more, the general framing of dark matter is it's called cold dark matter. So that means the nature of the particle, we think, that forms dark matter was that it was moving subrelativistically early in the universe when these particles became free to start exerting their force by gravity. And we also think that the dark matter does not interact with electromagnetic radiation, and it will only interact with itself and with other dark matter particles by gravity. So if that is wrong, if for some reason our understanding of the dark matter particle is wrong and it has other interactions, then of course the gravity calculations will be wrong. So there are two things people have investigated at some level. One is whether there are possible dark matter particles where there are other interactions or self-interactions, interactions between the particles themselves that affect how it behaves, that might mimic a gravitational effect. And then of course the other is our theory of gravity correct? Because largely we're talking about gravity theory in a realm that's not been directly tested. Newton's theory applies well within the solar system and is only really tested there. It's not tested on scales of galaxies, and the rotation and stellar orbits of galaxies that indicate a large amount of dark matter are predicated on Newton's theory of gravity, the inverse square law of gravity applying on those large scales. If that's wrong, because our gravity theory is wrong, if the force law has to be adjusted or on these large scales, for example, then all bets are off, and actually you can do away with the need for dark matter. And there's a thing called MOND, modified orbital Newtonian dynamics, which tries to adjust the Newtonian theory to get rid of the need for dark matter. it's a difficult thing to do theoretically without having other problems in physics, and some people think MOND is not favored by observations either. But these are both active areas of exploration.
All right, so we're 15 minutes in or 10 minutes in, so and everybody's chomping at the bit to talk about the Nobel Prize. So several people have asked if you could talk about the significance of the contributions by the astronomers that were recognized today. So I'll just let you go ahead and kind of riff on that for a little bit.
Sure. So I'll sort of separate this into several questions so I can cleanly demarcate the different contributions. So first of all, what was the Nobel Prize announcement earlier today, middle of the night in the United States? The Nobel Prize Committee awarded a prize to 3 scientists for studies of black holes, for investigations of black holes. One is a theorist, Roger Penrose, works at the University of Oxford, and the other 2 are observational astronomers, Reinhard Genzel, who's the director of a Max Planck Institute in Germany, and Andrea Ghez, who's a professor of astronomy at UCLA. Andrea Ghez, incidentally, I know her very well. She was a postdoc at University of Arizona some years ago. She's a superstar. She's had many prizes. So that's the short story. It was the awarding for investigations of black holes. And for the Nobel Prize Committee to give an award for black holes is, of course, a reflection of the fact that in the views of the scientists who make these nominations, black holes are real. They are not speculative, because remember, the Nobel Prize stipulation from Alfred Nobel's will is that the Nobel Prize has to be made for discoveries, for actual discoveries that further our knowledge. So if astronomers or scientists in general thought that black holes were still speculative and uncertain, we don't know if they exist or not, you wouldn't have a Nobel Prize for it. So the first thing I would say, and the first part of my talking about this, is to say that this Nobel Prize just indicates the level at which scientists are extremely confident that black holes exist. So that's the first thing I would say. Now let me sort of answer the separate questions of what these people actually did to warrant the prize. We'll start with the theoretical prize. So the prize was split between 3 people, but it was actually split unevenly. It was half of the award, the monetary award, which is well over $1 million now, was given to Roger Penrose. And the other half was split by the 2 observers, because they essentially worked on the same project at different locations. So we'll start with Penrose. Roger Penrose is a highly esteemed mathematician and theoretical physicist. He's worked at the University of Oxford most of his life. He's quite old. He's retired, but extremely active, and he's done foundational works in many areas. He's one of the world's best mathematicians. He got a Nobel Prize here in physics, but he's extremely well known to the mathematics community. And those of you who are interested in geometry are probably aware of a thing called Penrose tilings. So Penrose investigated sort of symmetry patterns and geometry patterns in math, and that led to a series of sort of tiling theorems of how you can rotate symmetric, different shaped objects and tile a uniform surface. That's kind of very basic geometric proofs in mathematics, and he's done other forms of mathematics. So he's right at the top of the mathematics profession. But he won this for physics, and his physics started in the mid-1960s when he worked with someone also very well known, Stephen Hawking, and they worked together on the theories of black holes. They really were doing foundational work in general relativity. And Hawking and Penrose wrote an incredible book about space-time and general relativity that's sort of became the textbook on the subject for decades. And they developed a series of theorems out of general relativity. They're called the singularity theorems. And they argue that black holes do exist, and that the singularities at their centers, these infinite situations of mass density, are inevitable results of general relativity applied to a collapsed stellar object. And these singularity theorems still stand. And so Penrose on his own, and then also working with Hawking, they were a formidable team actually, developed a lot of the theory of black holes as we currently understand them. So this is amazing work. Penrose also had other contributions. He, for instance, proposed a mechanism by which you could extract energy from a rotating black hole by sending particles or probes into the ergosphere, the region where there are trapped photon orbits, and then extracting that energy by essentially tapping on the angular momentum of the black hole and spinning it down. So the object you send in is a probe that does come out, because it doesn't go through the event horizon, but it does come out with extra energy that you can tap. Very clever idea. So he's close to what we would call the genius level, I would think, Penrose. And then to answer a separate question about the other part of the prize, because there's a different type of work, the other half of the Nobel Prize was given to Reinhard Genzel and Andrea Ghez. They've been fierce competitors for most of their careers, because they were working on this very important project to try and decide whether the center of our galaxy had a black hole. There was speculation about about all galaxies having black holes. It goes back to the 60s and even work of Penrose and Hawking. But evidence for black holes in any galaxy was rather indirect. I work on quasars, and those are supermassive black holes at the center of distant galaxies. And there's pretty good indirect evidence that black holes are in the center of all galaxies. But starting in the 70s and 80s with infrared imaging techniques that could see to the center of our galaxy, which is opaque to visible light. You can't get visible light from the center of our galaxy. There's an extremely compact radio source called Sagittarius A star. And these two groups, one under Genzel at the Max Planck Institute in Germany and one under Ghez at UCLA using the Keck telescope in Hawaii, they started to image the very central region, and they were looking at the orbits of individual stars, day by day, month by month, year by year. In the end, they gathered a decade's worth of data before they each group, working at different telescopes, showed that the orbits of individual stars near the center of our galaxy can only be explained by a massive black hole, about 4 million times the mass of the sun. So this was the nature of the work they did. And as I said, it did not happen overnight. This is not a discovery with an aha moment. This was a relentless observing campaign with exquisite observational techniques applied, a lot of dedication and persistence, and then eventually an interpretation simultaneously arrived by both research groups. Like I say, they were in pretty bitter competition at times, but they both got the same answer, the same method, using different telescopes and different instruments, and so they share the prize, as is appropriate, in fact.
One of our live viewers would like to know if you could talk a little bit about the difference between astronomy and astrophysics and physics, and cosmology, sorry.
Right. I mean, astronomy, I'll start with the difference between astronomy and astrophysics. They're kind of related, obviously. They're not completely different. Traditionally, astronomy refers very generally to the study of objects in the sky. So the objects in the sky, the stars, the planets, the phenomena of the night sky, and then on into the universe of galaxies and so on. So astronomy is now a term that brackets all of the objects in the universe that we can study observationally. So it tends to be an observational pitch or tilt to the subject. Astrophysics, by its hyphenation of astronomy and physics, is obviously the application of physics to astronomy. It's this quite simple way of explaining that word. And that means you are actually trying to understand the phenomena of the sky, the way stars work, the way galaxies work, how the universe behaves, shape of space-time, whether black holes exist, etc. And so astrophysics is a little more technical because it implies the use of physics to understand phenomena in the universe. And it is a large term too. And I would, as an example, there are degrees, PhDs in astronomy around the country in the US, and some of those departments award degrees in astronomy, PhDs, we do in Arizona, and some departments choose to call it a PhD in astrophysics, but really in the end it's the same thing. Now cosmology is a different term entirely. Cosmology really only refers to the study of the universe as a whole, and that's the definition of cosmology.
Several people, including Dennis, a baller who's on with us live, have noted that the 2017 Nobel Prize all went for the LIGO detection, and they would like to know how many physics Nobel Prizes have been given for work in astronomy and astrophysics.
Right. Well, that's a good question, and I came a little prepared. I don't have all this committed to memory, so I'm going to put my readers on in a minute. But yes, this is an interesting cultural issue. So the question of how do astronomers or astronomy discoveries get a Nobel Prize in physics? So I'll just start with that general question because that's an interesting question that some scientists and other people wonder. You know, the subjects of the Nobel Prizes were determined by the quirkiness of Alfred Nobel. The Nobel Prizes started essentially in 1900. Max Planck was the first to win the physics prize. And those subjects were determined by Alfred Nobel's will. And there were some significant omissions based on the time. And so other fields have had to make their own arrangements. Well, one of the great omissions was mathematics. I mean, it's a really important subject of intellectual study. And so mathematics has developed its own prize called the Wolf Medal, which is just as reputable and almost as valuable as a Nobel Prize, but because Nobel didn't put a mathematics prize. And in fact, the Nobel Prizes were pitched as being about discoveries. And so intrinsically, the Nobel Prize description sort of discriminated against theories. So the development of a theory on its own, even if it's validated by observation, doesn't necessarily merit a prize, whereas a discovery of a new type of object or a new phenomena or a new mechanism in biology does merit a prize. And so the history of the Nobel Prizes in science is definitely skewed towards observation and experiment. And again, the subjects are rather particular. For instance, you know that in addition to all the science prizes, there's an economics Nobel Prize that was added later, a few decades later, I think. It hasn't been in existence since 1900. And there was also a Nobel Peace Prize. Very ironic, given that Nobel was the man who made his fortune from gunpowder and explosives. This was maybe him trying to repair his reputation in history. So that's the general scenario of the Nobel Prizes. And the more particular part is, where does astronomy fit in terms of the physics prize? And the answer is, for a long time it didn't. For a long time the physics prize really just went to things like quantum theory, solid state physics, plasma physics, various other clear forms of physics where the experiments were done in a lab or at accelerators and so on. So for decades the prizes were awarded that way. So I'll treat as a separate question, and now I'll answer the question, how many Nobel Prizes in physics have gone for astronomy or astrophysics, now that we've seen they're essentially the same thing. So again, for a long time, the answer was 0. And as in my count of it, 10 Nobel Prizes in the history of the physics prize, which goes back to 1900 and Max Planck, have been given for astronomy or astrophysics. And the first wasn't until 1974. So it's a fairly recent phenomena, and basically the Nobel Prize committee, the physicists who obviously award the prize, had to broaden their scope to include astronomy. I don't know whether they thought astronomy was suspect or they didn't trust the observations of astronomy because it's not the same as being in a laboratory. It's not clear. There was a cultural issue at play there. And some astronomers have felt that even in the first couple of decades after the prize was awarded to astronomy for the first time, astronomy was a little bit neglected because there were a lot of discoveries in astronomy through that time. So I'll just take a minute, and I know most of these to memory, but to get them all right, I'm going to put my readers on and tell you that the first was for pulsars. That was the discovery that Jocelyn Bell essentially was excluded from the Nobel Prize, controversial, 1974. So that was the first Nobel Prize in physics that went to astronomy. The next one was 4 years later, 1978, to Penzias and Wilson for the discovery of the microwave background, a discovery made in 1964. So it took 14 years for them to get that award, and as we'll see, the more recent awards to astronomy have come much more quickly after the discovery. You don't have to wait quite that long. Remember, to win a Nobel Prize, you have to be alive. So if you die before they get around to you, that's too bad. The next one was almost a decade later, 1983, when it went for the theories of the chemical evolution of stars, how the heavy elements are produced in stars. Willie Fowler, who I met at Caltech when I was a postdoc there, was one of the recipients of that prize. And then you have to wait another decade before the next astronomy prize, and that goes again for pulsars, this time to Hulson-Taylor, who used radio techniques and pulsar systems to show that gravitational radiation or gravity waves exist. That wasn't the detection of LIGO. That was just a very clever experiment to show that that prediction of general relativity was true. So that's 1993. Then you move forward again another decade, and Riccardo Giacconi shares a prize with other lab physicists for X-ray astronomy, pioneering X-ray astronomy. And so in that first few decades, you only have 5 prizes. Now the next 5 haven't taken as long. In 2006, a second prize was given for the microwave background for the work of the COBE satellite and the people that led that team. Then 5 years later, in 2011, the Nobel Prize was given to 3 physicists, one of whom was an undergraduate in Arizona, Brian Schmidt, the other 2, Adam Rees and Sol Perlmutter, for the discovery of the accelerating universe, dark energy essentially. And that's 2011, and now, very interesting, we've had 3 out of the last 4 Nobel Prizes in physics go to astronomy. In 2017, LIGO, the discovery, the detection of gravitational waves. In 2019, last year, for cosmology to Jim Peebles, and for the discovery of exoplanets to Michel Mayor and Didier Queloz out of the University of Geneva, and then this year for black holes. So I'd say astronomy is kind of surging in the Nobel Prizes, with 3 in the last 4 years and only 10 ever.
Wow, that is amazing. Kind of going along with these black hole themed questions, Ritik is on with us live and would like to know, do black holes have an internal structure? And if so, is it ever possible that we might be able to probe the internal structure?
So the internal structure of black holes is still a matter of debate, and Penrose, Roger Penrose, winner of this year's Nobel Prize, was really one of the first mathematicians or theoretical physicists to write meaningfully about the internal structure of a black hole. It was Penrose that recognized that there had to be, inevitably, in the general relativity, singularity at the center of a black hole. These were, in other words, it's a feature, not a bug of the theory. It's a prediction. It's not easy to understand the nature of a singularity. He also, out of the singularity theorem, showed that it would be unlikely in nature to have what he called a naked singularity. So he showed that the event horizon, which is the boundary to our knowledge, the region we can't see inside of, would always surround the singularity. So no naked singularities, an event horizon that surrounds a singularity. And as for the internal structure of a black hole, that's it. That's all that the theory predicts, and that's all that Penrose talked about in his writings and his articles. Now, people have speculated what the interior might be between the event horizon itself and the singularity, but we have no evidence, and the theory is not really giving us any hints.
A couple of people have pointed out that the Fields Medal is sort of the mathematics equivalent to the Nobel Prize. Is that, could you comment on whether that's seen as prestigious, or where that rates?
Yeah, I realize I misspoke. I said the Wolf Prize. I meant the Field Medal. Yes. So the question is about the Field Medal, and yes, the Field Medal was developed and funded pretty much as a recognition that the Nobel Prizes should have been given to mathematics as a subject, but it wasn't part of Nobel's will. And so instead you have economics, but you don't have mathematics. That seems a little arbitrary. And so the Field Medal, absolutely, in monetary value, in prestige, in the nature of the discoveries or work that it recognizes, in that community and in science and technical terms broadly, is absolutely as prestigious as the Nobel Prize. I don't think there's any doubt about it. The list of Field Prize winners is incredible in terms of the people it recognizes. Now, the world has invented other prizes. There's the Shaw Prize now, the Wolf Prize, the Breakthrough Prize. There are some prizes that are all in that $1 million category, so they're high monetary value and high prestige, that have also come in, and some of those prizes recognize fields that the Nobel Prize does as well. But math needed its own prize, and in fact, it got it.
Jeffrey Needle, who's on with us live, says, I'm interested in the rare Earth hypothesis. Can you talk about what that is and what is meant by the term rare in that case?
Right. The rare earth hypothesis has been around a couple of decades. Um, and I was on sabbatical in University of Washington where Don Brownlee works. And Peter Ward and Don Brownlee wrote a quite good popular book that summarized what their research articles had talked about. And it was called Rare Earth. So if you want to read a whole book on it, you can. It's a little out of date now, but it's very well written. So what is the gist of the rare earth? The gist of the rare earth is an argument in a number of pieces for the likelihood that complex life, by which I might mean multicellular or life that develops, brains and intelligence and technology, is rare in the universe. So it's not speaking to the rarity of Earth-like planets, which at that time it was proposed we didn't have any evidence for. Now we do. We know there are a lot of Earth-like planets out there. It was really talking about the rarity of Earth as a host for complex life. And their argument was based on a number of pieces. And I can't elucidate them all. It would take a long time. But for example, the idea that the moon is a large object which stabilizes the orbit of the Earth and its axial tilt, and stops it from varying too much, as opposed to Mars, whose axial tilt and therefore the seasonal variations change a lot over time. So the Earth as a stabilizing influence on the Earth, as a cause of tides, which could be implicated in life, and then various other things, such as the particular size and mass of the Earth that gives rise to plate tectonics. There's the idea that you need plate tectonics for life, and so if your planet's not quite big enough and has no molten core, you won't have life. And they piece together a series of attributes of the Earth, our planet, that they argued would be statistically rare among planets. And therefore, complex life was likely to be rare, just because even if there were a lot of planets out there, there would not be many that had the particular attributes of the Earth. Why was this idea unpopular? Well, it was unpopular. It wasn't uniformly unpopular, but there was pushback against it. I think most astrobiologists and astronomers just thought they overplayed the argument. Also, they combined independent pieces of evidence that weren't always independent to make their case. And some of their arguments have sort of got weaker over time. It's simply not clear that all the attributes they said were rare about the Earth were necessary or sufficient for complex life to develop. So that sort of weakens their overall case. And I think the jury is actually still out on this, because of course we don't know about life anywhere else, and we certainly don't know how likely that life is to persist for billions of years and get complex. So I think it's in the category of a provocative idea that has significant merit, that got people thinking a lot about foundational issues in astrobiology, but probably in general most astrobiologists don't hold to that hypothesis.
Excellent, thank you very much. The next question is from Stephen, who sent an email. With all of the interest being shown in Mars at the moment, also to a degree the moon, is there any cooperation between the various countries with the result from several orbiters and landers, or is it a case of the cat that licked all of the cream, which I'm guessing is the saying that if you get there first, it's yours?
There is both competition and cooperation. The competition is most clear with China. There's no question that China wants to do everything themselves. They want to develop their own technology. They've had, from a slow start of their space program, they've accelerated their launch capabilities and their rockets to put people in orbit. They've had a lunar rover, they're planning a moon base, they're planning a Mars base, they're planning a space station. So they're trying to do it all themselves, and they don't really need or want to cooperate with anyone. So in that case, it's pure competition. The Soviets, the Russians, have had to trim their sails based on their circumstance. I mean, Russia is not a very wealthy country anymore, and although they led the space race from the first 2 decades, pretty much reaching all the landmarks first, since the fall of the Soviet Union, the country is fairly poor. They have a huge military-industrial complex still, a lot of nuclear weapons, and a lot of capability. But they're still using the Soyuz rocket from the 1950s and 60s, pretty much unaltered. So the Russians have rather limited capabilities in this regard. And then the rest of the countries are pretty much not competing, they're cooperating. So the Europeans and the Americans have cooperated on space programs and space telescope, the Hubble Space Telescope, for example, and a lot of very frontier space facilities for a long time. And they've cooperated. They've sort of partially cooperated and partially competed on Mars, I would say. But for more ambitious things like sample return and a base, they're almost certainly going to cooperate because these are very expensive, difficult undertakings. And the other player, the other very significant player in this is Japan. Japan has wanted to develop its own space capability and has its own, robust space astronomy and satellite program. But for larger ventures like the Moon and Mars, they almost certainly will be collaborators and helping. And so Japan, Europe, and America are going to combine forces to do the most ambitious things on Moon and Mars. The other two spacefaring countries that are up and coming and have some national pride in doing things themselves and not with others are Brazil and India. But India, of course, has had a moon mission, and India has quite a lot of ambitions. And they, again, want, out of national pride reasons, to make their first forays on themselves. But I think in the end, they might cooperate too. So it's that mix of cooperation and competition.
Excellent. Thank you very much. The next question is from Hilda Chinchilla, who is on with us live, who would like to know if you can explain quarks and then subsequently quark stars.
Right. So quarks were a prediction. They were a prediction from the 1960s in fundamental physics for the constituent particles of protons and neutrons. And so Nobel Prize, when they were eventually indirectly detected in the 1970s, Nobel Prize went to Murray Gell-Mann, who was the person who dubbed them quarks. And it's a famous story that the word quark, the Germans didn't actually like this because in Germany, especially in southern Germany, quark is a colloquial word for a kind of sour milk. That's not a very nice word in Germany. But Gell-Mann, who's extremely well-read polymath physicist, he took it from a phrase in James Joyce's almost unreadable book, Finnegan's Wake, 3 quarks for Mr. Fark. I mean, it's just one line in a long, rambling, dense, almost impenetrable book. But Gell-Mann was showing his erudition by naming them quarks, and he got to do it because he was foundational in the theory of quarks. And so in those experiments, those high-energy physics experiments, it was shown that quarks are fractionally charged particles, and they cannot exist singly, and so we have no single quarks in nature. They cannot be liberated except for tiny fractions of a second from an atomic nucleus. But in combination, they reach unit or integer electric charges, and when they combine in 2 quarks, you get leptons or light particles, and when they combine 3 at a time, you get neutrons and protons, and so the core constituents of matter. And so quarks are foundational particles in high-energy physics, and we've learned a lot about their properties. The puzzlement, of course, is that there are 3 families of quarks, 2 pairs of quarks times 3. So there's the up and the down quarks, and all normal matter, neutrons and protons, are made of up and down quarks in different combinations. And then there were strange and charm quarks, which have slightly higher masses or energies. And then there were the top and bottom quarks. And now they've all been found. And Nobel Prizes were awarded. I think there have been 5 or 6 Nobel Prizes for quark experiments at high-energy accelerators around the world. Quark stars are a prediction, a theoretical prediction. In certain massive stars, it's possible that at the late stages of the evolution, but before they are entombed as a black hole or a neutron star, the densities might be sufficient and the temperature is sufficient for the quark soup to exist. In other words, the quarks that are not normally freely moving around in the world and are very hard to see except for tiny fractions of a second, in the conditions at the core of a massive star, the quarks could be liberated to move around freely, and so their interactions with each other and with the rest of the star could have a significant effect on the nature of the star. And so people are trying to show experimentally or observationally whether quark stars or quark matter in stars actually exists. And I think at the moment that's not been proven.
Thank you very much. The next question is from Subham, who sent an email. I would like to know about the feasibility of placing a space-based solar power module in orbit around the Earth, say L1 point. What are the pros and cons of something like that? Transmitting to power to the Earth via microwaves.
I think it's completely feasible. These technologies have been, they haven't really been prototyped, unfortunately, but the theory of how to do that has been around for a while. So it is indeed possible to put a very large solar concentrator at a Lagrange point. L1 would be fine, and you'd have to unfurl a sort of gossamer thin membrane of reflective material that could act as a concentrator, and then you can deflect that and convert that into a microwave beam that you beam back to the Earth, and then when it arrives, of course, you convert that radiant electromagnetic energy into power. I mean, either by, well, there are various ways to do it. It could drive a turbine indirectly, like in a power station, or it could be used to vaporize material that you then condense and get the energy back out. There are various ways to do it. So yes, the technology to do that certainly exists. It's not clear, however, whether building a sufficiently large solar concentrator to have a real impact on Earth energy requirements, whether that would put you at the break-even point for the cost of energy. Unfortunately, for our attempts to get liberated from fossil fuels, coal is getting expensive, but oil and gas are still very cheap. And there's still a lot of oil and gas in the ground that people are digging up, and more reserves that they're finding every year. So and while electric and renewable sources of energy are now getting cheap enough to compete with oil and gas, these exotic forms of power from solar concentrators and microwave beams, the infrastructure and startup and capital costs are so high that they don't really project to break-even costs at the moment. So that's a challenge, and basically that means these projects won't happen probably for a while until the situation changes.
The next question is from Robert. The discovery of phosphine on Venus is still kind of a hot topic and on a lot of people's minds. How likely would you say that the phosphine found on Venus indicates life? And how would we kind of definitively find or prove that it was created by living organisms?
I would say, realistically, it's an exciting discovery and deserved the attention it's got. But, if I were to put a number on it, I'd say the odds that it truly indicates biology in the Venusian atmosphere are 10 or 20%. They're fairly low because we simply don't know enough. All we know is that phosphine on Earth is implicated in biological mechanisms and biological organisms, but we don't even know how it's used, how it plays into a metabolism on the Earth. So it's a little bit of a stretch then to go to a very alien and extreme environment and say that it indicates biology. So that's one big omission. I think the real omission is that we just don't have enough data. Knowing that phosphine exists in certain levels of the Venusian atmosphere is one thing, but you have to know all the chemistry of that layer of the atmosphere. So you'd have to have very detailed measurements of the density and the temperature and the turbulent patterns and the interaction rates of different molecules, and also the concentrations of other trace molecules that are important in, say, a chemical network, before you could even speculate that there might be biology emerging from that. So it's going to take more than we can do with current observational capabilities. It's obviously going to take a probe sent to Venus to learn substantially more. And those plans are underway, actually, but it'll take a couple of years before that can be sent out.
Kind of related, what are the odds of finding life on Mars, and what kind of work needs to be done to sort of definitively prove life on Mars? Are there enough ways to gather different pieces of indirect evidence, or does it need to be a direct observation like with a microscope?
It's a good question. So what I think the odds of life on Mars now, existing life on Mars, they're low, but they're not as low as I would put for Venus. They're maybe 30%, 40%. I think it's a good chance that there's life right now, not on Mars, but in Mars, under the surface of Mars, in subsurface aquifers with energy sources from just radioactive decay or just from the pressure of the rocky material on a liquid underneath it. And the ingredients are all there. We know the carbon-rich materials there, local energy sources, and liquid water. They're all there. So what would it take to show that? Well, that's a problem. So what the rovers, even the current rovers and the next generation of rovers can do is just scratch around on the surface and do chemical analysis. But nobody really expects life to be found on the surface. And if we find fossilized versions of life, they're undoubtedly going to be very subtle microbial forms of life, the kind we had on the Earth. First life formed 4 billion years ago, and the earliest good evidence for life is 3.7 billion years. And there you're just looking at slight chemical imbalances of metabolized carbon versus a radioactive form of carbon, neutral, normal carbon versus radioactive carbon, for example, and how they metabolize, and then that ratio varies. Those are very indirect ways we find life on Earth, and we'd be using those same methods on Mars. And just as on Earth, they would be controversial, the claims of life, because you're not looking at fossils you could see, certainly not by eye, and maybe not even with a microscope. So without actually finding body fossils, if you like, in the Martian soil with rovers, then that's not going to be sufficient evidence. Nor can we find the material that we could subject to sort of PCR methods. A polymerase chain reaction is a way of amplifying small amounts of DNA or RNA and boosting them up so that they're easily detectable and you can study them. So yes, if we found nucleic acids or chains of nucleic acids or the significant components of the biological basis of life on Earth, on Mars, that would be convincing. But again, no experiment that's currently on Mars or planned in the near term is going to be able to do that. It's actually going to take a next generation of experiments, and it's probably going to take a generation of experiments that are able to drill fairly deep under Mars and find an aquifer to really find life and study it where it lives, meters down, maybe tens of meters down. That's quite challenging. So I think we're a decade or more away from any potential evidence of life on Mars that will be truly convincing.
The next question is from Fairy Tale Fan, who is on with us live, who would like to know if you can talk about the Higgs boson and what is it exactly?
The Higgs boson is a particle that completes the standard model of particle physics. So the standard model of particle physics is a schema by which we understand the relationship between heavy particles and light particles, by which we arrange these particles into various families that have different masses, and we associate these particles with 4 forces of nature, each of which have their own particles that carry those forces. That's, in a nutshell, the standard model of particle physics. But what the standard model of particle physics says nothing about is why do the particles all have different masses, or how do they have different masses? Why are the electrons roughly 2,000 times less massive than neutrons and protons? Why are there intermediate mass particles like muons? Why are the quarks all of different masses and in 3 different categories of mass and 3 families? Standard model doesn't say anything about this. Now the Higgs particle doesn't explain all the specific masses of all the particles, but it provides a mechanism by which all the particles have mass in the first place. So it's a sort of mass generation mechanism. And what it really is a hypothesis of a field, that is to say, a sort of energy essence that's ambient in space, that the interaction of that field with a particle is what generates its mass. If you want to think of it as viscous drag in this field, and the particles that have a larger viscous force and drag are more massive, and the ones that have less viscous force and drag are less massive, that's a fair way of thinking about it. And so it's really a field, and it has an associated particle that's called the Higgs boson. The theory of the Higgs was developed by, obviously, Peter Higgs, a professor of the University of Edinburgh, who won the Nobel Prize when the particle was discovered in 2013 and 2012 at CERN. And it was found at an energy at CERN of about 130 giga-electron volts, and that's exactly in the narrow range that was predicted by the theory. So it was a stunning confirmation of a theory that really dated back to the 1960s that was foundational in high-energy physics. And the detection of the Higgs particle, the Higgs boson, and the associated Higgs field is a capstone of the standard model of particle physics. But it doesn't explain everything. It's just a very important piece of the picture of how particles get their properties.
Excellent, thank you very much. Incandescent World would like to know if you can explain why there are missing baryons in the cosmos that are regular matter when only 5% of regular matter takes up the cosmos and 95% is dark matter. I think those ratios are, off. But can you talk about, dark matter and these missing baryons?
Right. So let me talk about the missing baryon problem, because it was viewed as a problem for some time, and I think it's been almost solved. The missing baryon problem is that the sort of cosmic pie of what the universe is made of is in roughly 3 pieces. It's roughly 2/3 dark energy, which is causing the accelerating expansion of the universe, about 1/3 dark matter, which is the subatomic particle, we think, not yet discovered, which really holds galaxies together and which dominates normal matter, the stuff we're made of, by a factor of 5 or 6. And then there's normal matter, the so-called baryons. And the amount of baryons in that pie chart is about 5%, 4 or 5% of the cosmic pie. And very nicely, that fraction of baryons in the universe is completely consistent with Big Bang theory, the theory of the hot universe and how it started. So that's a nice consistency, if you like, with the baryon fraction of the universe we see and the Big Bang theory itself. But when we go out and look for the 5% of the universe that's in baryons, according to the theory, it's very hard to identify them. And in fact, only 1 in 5 of them were found for a long time. So we had 1%, which is to say all the stars and all the galaxies that we can count, and we can count them all basically with big telescopes, only account for 1% of the matter of the universe. And that's only 1 part in 5 of the baryons. So where is the rest? Where are the other 80%? The other 4% of the universe, essentially. And that's a missing baryon problem. But it was also clear right around the 1970s and into the 80s that some large fraction of the baryons were likely not to be in stars and galaxies, but to be in a very diffuse, hot medium between galaxies, the so-called intergalactic medium. So the medium between galaxies is not a complete vacuum. It's a very diffuse medium, but it has a significant density. And more importantly, because of the ultraviolet radiation from stars, that radiation keeps that diffuse plasma extremely hot, hundreds of thousands or 1,000,000 Kelvin. And that means the only way you could see that plasma is in X-rays. And we never had good enough X-ray telescopes until recently to see this diffuse medium between galaxies that doesn't shine in visible light, that's why they're invisible baryons, but would shine in X-rays. And actually it took some very clever indirect experiments to show that these baryons did exist, that they are hot, and that they do make themselves known in X-rays. So I wouldn't say that it's all been tied up neatly with a bow, but there's pretty compelling evidence that that missing baryon component of the universe is very broadly and smoothly distributed in a hot, rarefied medium between galaxies.
The next question is from Varun, who has kind of an interesting hypothetical question and idea. And it's basically about the relationship between energy and mass. So we know that light is massless, but it has energy, and energy and mass are sort of the same thing. Could you possibly take enough energy or light and condense it or focus it into a small region and form a massive body like a black hole?
It's an interesting question, and it's a matter of technology, actually. But because yes, mass and energy are equivalent. E equals mc squared is the definition of that equivalence from Einstein, and we can make that equation go in both directions. It's possible to liberate energy from pure mass, and the simplest ways we found to do that are with the fission and fusion processes. And it's also possible to take pure energy and make mass. And the simplest way to do that is when in an accelerator, for example, we deposit a huge amount of kinetic energy and turn that into the creation of particles and antiparticle pairs. So that can be done. The question is, can you make a material object that way? And I think the answer is no, because you need an enormous amount of energy to create a tiny amount of mass. That's the c squared that multiplies mass in E equals mc squared. And so that sort of tells you the answer, that it's simply too much energy required to create a sufficient amount of mass to make a real material object. You can create it at the level of subatomic particles, and maybe a number of those, maybe hundreds of those. But at some point, you just need too much energy to make a material object of any significant size. So at the moment, the answer is no, we can't do that.
The next question from one of our live viewers, they would like to know if gravitational waves have frequencies like light waves do.
Yes, they have frequencies. Not quite the same as electromagnetic radiation, because with electromagnetic radiation, the oscillating electric and magnetic fields propagate at the speed of light, and associated with their oscillation, they have a frequency and a wavelength, and that's how we think of light, for example. Gravitational waves are different. They also propagate at the speed of light, we think. That's not actually proven, but that's what the theory says, and everything we know is consistent with that. And they do have a wavelength, which is the wavelength at which they oscillate or undulate or distort space-time. And in fact, LIGO, the detector that's been used to detect gravitational waves, can only look at certain wavelengths of gravitational waves, or frequencies, remember they're equivalent. And in LIGO, they tend to work in terms of the frequency. So LIGO is sensitive to frequencies of gravitational waves in the range of about 10 or 20 hertz, or cycles per second, oscillations of space-time per second, up to several hundred, maybe 400 or 500 oscillations per second. Higher than that, LIGO has a noise limit where just electron noise in semiconductor detectors, so-called shot noise, dominates, and so you can't detect the very high frequency gravity waves. And lower than about 10 hertz or 15 hertz, LIGO's detectors start to be confused by geological noise, just the shaking of the Earth, simple geological seismic waves of the same frequency. So that's the frequency range that gravitational waves can be detected currently. But nature will probably make gravity waves of all manner of frequencies, just like there's all manner of frequencies of light. The very largest black holes will make incredibly low frequency gravitational wave ripples when they combine or merge. And small objects will make more rapid ripples.
Excellent, thank you very much. We are at 11 o'clock at this point, so we'll run for a couple more minutes. Anas Syed, who's on with us live, would like to know if AGNs, active galactic nuclei, and quasars are the same thing.
Yes, they are related to each other. They're terms that astronomers use who study what in essence are supermassive black holes at the center of galaxies. So AGN is the more general term. It stands for active galactic nuclei, and it's basically just saying that as far as we know, every galaxy in the universe that we've studied so far has a massive black hole. The mass of the black hole seems to scale with the old stellar population in the galaxy. So the most massive black holes are in elliptical galaxies, and the least massive black holes are, of course, in dwarf galaxies or spiral galaxies. And so if all galaxies have black holes, the question is, why are they only active some fraction of the time? So the study of active galactic nuclei is trying to understand, first of all, what's going on with this incredible energy that comes out across the electromagnetic spectrum, where the nucleus, the black hole region, the vicinity of the black hole can outshine a galaxy by factors of hundreds. That's what an active galaxy is doing. But also, why does it not happen all the time? Why are active galaxies switched off perhaps 90 to 99% of the time, and when they're inactive, they don't shine brightly, and we barely know there's a black hole there. So that's active galactic nuclei in general. And galaxies called Seyfert galaxies are part of this category, this broad category. Radio galaxies, things that don't have bright optical emission but have strong radio waves, and radio jets are part of this. and even starburst galaxies where the starburst may be fueled by a black hole. So AGN is a category that includes all manner of phenomena associated with a black hole at the center of a galaxy. Quasar is a more specific term that relates to the most luminous and probably the most massive black holes in these galaxies. And when it's a quasar, it means it is in the active phase. So detecting it as a quasar means that this is a central object that is pumping out so much radiation that it outshines the surrounding galaxy by some large factor. And the word quasar is short for quasi-stellar radio source or quasi-stellar object, and that means they look star-like on the sky because it's not obvious there's a galaxy there. You're seeing the bright nucleus completely obliterating or outshining the surrounding galaxy, and often the galaxy is, these objects are far away, high redshift, large distance, so the galaxy itself is very faint, but the nucleus is so bright you can see it across the entire universe. So quasars are the more extreme form of active galactic nuclei. I spent a couple of decades of my career studying quasars, so I'm fond of them and pretty familiar with them.
Excellent. Thank you very much. The final question for today is, could you talk about if you know the reason why Venus and Uranus rotate in the direction in counter to the rest of the planets in the solar system, and then we'll wrap up.
Right. So of all the planets in the solar system, there's a lot of regularity. They almost all spin in the same sense that they orbit the sun, which means the angular momentum vectors are aligned. That would be the physics way of explaining it. And the two exceptions, and there's some moderate exception because they have orbital tilts, like the Earth, 23.5 degrees, and Mars even a little bit more. The two exceptions to this general rule are Venus, which counter-rotates, rotates in the opposite direction to the way it goes around the sun. So it's on its head, if you like. And Uranus, which is on its side, and it has an axial tilt of 87 degrees. It's essentially on its side. And the question is why? And there are really only two answers possible. One is that it was due to initial conditions, that they formed that way and they've just stayed that way. And that's rather unlikely because of the physics of how a rotating gas cloud collapses. So subregions of a rotating gas cloud, when they collapse, should share the angular momentum of the overall cloud. And that's why most planets rotate the way they do, the same sense as the way they orbit the sun. There's not obvious that you could have any turbulence or strange properties of the gravitational collapse that would exempt a couple of the planets from this situation. The second reason they could have this is for interactions, collisions, violent events that occurred after formation, and that's generally viewed as the explanation. And it would literally take something like an impact very early on, as violent, for example, as the impact of a Mars-sized object with the Earth that led to the formation of the Moon, to knock a planet on its side or on its head, which is colloquially what's happened to Uranus and Venus. And so that's what people think actually happened for those two planets. However, the problem with that explanation is, how do you prove it? Because that event almost certainly took place a long time ago, 4 billion plus years ago, close to the formation time. And evidence of the impactor has long gone, of course, and we also don't know how to study these objects up close enough to see evidence that they were hit, as opposed to the Earth and the Moon, where we can study that possible impact much better. So unfortunately, we're still left speculating about why they have these properties, but that's what the best guess is. So thank you again, lots of great questions, and I should say a very exciting and fun day in astronomy when the Nobel Prize in physics goes to astronomers. Especially, I know them; they're all really great researchers and nice people, and it's a well-deserved prize today. So thank you, and we'll be back with you, I think late next week.